Okay, in this lesson we are going to be reviewing some functions, some information about functions, and some domain and range. So remember that a function means that every element in the input, which is the domain or the x values, generates a unique output, which is the range or the y values. You can tell if something is a function by if it passes the vertical line test when you look at the graph. So remember that the domain is all the x's, the range is all the y's. A lot of this is review. So this is function notation. Um, we read y equals f of x, or the value of f at x. X is the independent variable, y is the dependent variable. Okay, so here is an example of something that is in function notation. The area of a square is a function of the length of its sides. And so f of s equals s squared. This basically is the area. Okay, and we'll kind of talk about this. One way to see if something is a function is to see if it passes the vertical line test, which is to draw a vertical line anywhere on the graph. And it can only cross the graph in one point. So these are graphs. If I graph a I draw a vertical line anywhere, it only ever crosses in one point. And so this does pass the vertical line test, and it is a function. This one also passes the vertical line test and it is a function, but this third one fails the vertical line test because it crosses in more than one point, and so this one is not a function. All right, so another way to tell is by looking at a mapping, by making sure that every x value only goes to one y value. So this one is a function here because every x only goes to one y. It's okay if more than one x goes to the same y, but when I leave this x value, it only goes one place in the y value. The difference here is this x goes to more than one y. So you have more than one line coming out of any one x value, and so that would make it not a function. You can also look to see whether things are functions kind of algebraically. Okay, one thing you could do is you could graph these. And just to let you know, if you don't know enough about this, this is an absolute value function. I'm not even going to take the time to graph them on my graphing calculator. It's an absolute value function, which hopefully you can remember. Absolute value functions look something like this. I did not graph that correctly at all, but just know that it's an absolute value function, which is V-shaped. So if you think about the graph of it, it should pass the vertical line test, which is a function. Okay, the other thing you can do is pick a number for x. Okay, so let's say I pick x is 1. Okay, then I want to think about what f of x is or what y would be. F of x you can think of as y. So when I do that, I get 2 times the absolute value of 3 times 1 plus 1, or 2 times the absolute value of 4, which is 2 times 4, which is 8. And there is no other answer that I can get. So one input gave me one output, and so I know it's a function. That's different over here, by the way. If you can see this, when you have a y squared, hopefully you remember that it makes a graph that's a sideways parabola. So certainly you could graph that on your graphing calculators and graph that and realize it's not going to pass the vertical line test. But algebraically, let's say I pick x to be 1 again. And you can pick any number for x, it doesn't matter. But if x is 1, then f of x, which happens to be y squared. I should do this. Y squared is 1 plus 3, so y squared is 4, which means y could be either 2 or -2. That satisfies that equation. So when x is 1, y could be 2, or when x is 1, y could be -2. And hopefully you can see that you have one input for your x, but you have two outputs for your y. And you can't have that, okay? One input cannot generate more than one output. So it is not a function. Okay, so again, your domain is your set of all of the x's that can possibly happen. Some things you need to watch for when you do this is square roots. You cannot have negative quantities underneath any radicals, or any even-powered radical, I should say. And you cannot have zeros in the denominator. So those are some kind of key things that you need to watch for when you're doing domain and range problems. Okay, this is just a graph, so we're going to look at the domain and the range here just to get used to how to write the notation for it. Okay, so remember that domain is your x value, so you want to look at what's happening as you move left to right on that graph. And so if I think about drawing kind of a vertical line and seeing where that line starts to hit the graph, it starts to hit the graph right here when your x value is at -5. Make sure you're using x values, and it continues to hit it and 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 hit it all the way to over here when your x value gets to be 6. Okay, so I can write that a couple of different ways. I can use interval notation, and you're going to use a bracket for when it's equal. So it would go from -6 until it goes from -5 until it hits 6. And it's at exactly -5 and at exactly 6. That's interval notation. Because they're exactly -5 and exactly 6, I have a bracket. If it was an open circle on either of those ends, then I would have a parentheses surrounding that instead of a bracket. But that's one way to write it. Or I can write it in set notation, the set of all x such that your x values are between -5 and 6. Greater than or equal to, because again, those are closed circles. Okay, so that's your domain. Your range then would be to go and look at your y values. Okay, so not hitting the graph, not hitting the graph, not hitting the graph, but I start to hit the graph right there when my y value right here is at -6, all the way until my y value is right here at +2. Okay, so your range would look something like this: -6 to +2, or I could go set of all y's such that, again, your y value has to be less than or equal to -6, less than or equal to 2. Okay, that's how it goes. All right, and then we're going to do this one together too. And I think we're going to skip that third one just in the interest of time. This one has kind of two things that you're working on. It's a little hard to tell if these are open or closed circles. We don't really know, quite honestly, and we're kind of estimating, and it's not marked for us. So we're just going to pretend that they're open circles, okay? I probably should have marked these for us, but I didn't. We're going to pretend they're open circles, okay? So here we go. Your domain, if you were to do this problem, your domain as you move across, I start to hit it when my x values are about -6 until I hit about -1. Okay, so my domain is going to look something like this. Open circles, -6 to -1. And then I take a little break in the action when my line is between here and here. It's not hitting the graph, but then it hits the graph when x is about 0. So I need a union in there. About 0 to about 6. Okay. In set notation, it would look like this. Set of all x such that x is between -1 and, -6 and -1, or x is between 0 and 6. Okay, notice they're not underlined because they're brackets. Okay, so that's your domain. Then your range, sorry, I need to flip that baby. It won't flip for me. There we go. Your range, if you go this way, starts when your y value is -3 until your y value is 1. Then I take a break, and then for this line, your y value remains constant at 3. So your range would go -3 to 1, union exactly 3 with a bracket, okay? And in set notation, set of all y such that y is between -3 and 1, or it equals 3. Okay? So that's how that rolls. All right, this one we're going to skip, I think. By the way, this will go to infinity, positive infinity, okay, just to do that. All right, now we need to get into some algebraic ones where we deal with domain and range just algebraically, and we are not, or just domain, I'm sorry, we're going to do this just domain, and we are not going to graph it, okay? So some things you need to watch for. So first of all, you cannot have negative numbers underneath the radical, okay? So this quantity here better be greater than 0. The smallest number you can have underneath the radical is greater than, or is exactly 0. So that means that x minus 3 has to be greater than or equal to 0, which makes x greater than or equal to 3. Okay? Down here, I can't have a 0 in the denominator, so I need to figure out what would I have to plug in for x to make my denominator be 0. So I'm going to set it equal to 0 and solve it. So I would subtract 1, divide by 2, and x equals -1/2. So if x is -1/2, that means that my denominator would be 0, and I can't have that, okay? X can't be -1/2. Now, here's the deal. Up here, I'm already restricted to numbers that are greater than 3. -1/2 down here is not greater than 3. So because I'm already restricted to numbers that are greater than 3, quite honestly, this doesn't even matter. Okay, I have to have numbers that are greater than 3. And sometimes you might have to put a kind of a number that you would skip in there. In this case, I don't. So in this case, my domain would be set of all x such that x is greater than or equal to 3. Or if you do it in interval notation, 3 to positive infinity. Okay, on the next one, let's see, I think I changed this, so it's not where it needs to be. I did. Okay, so let's change this one. Let's do the square root of x over x minus 5. Sorry, I'm going to just change this. All right. Okay. Right here, I know that x needs to be greater than 0. Okay, x has to be greater than or equal to 0, I should say, because I can't have negatives underneath the radical. Right here, x can't be 5, because if x is 5, then I have 5 minus 5, which is 0 in the denominator. Okay, so what I have here is that this tells me that I have to have numbers that are all greater than or equal to 0, but I have to exclude the number x equals 5. So here's how that's going to look like, okay, or what this is going to look like. Your domain would be set of all x such that x is greater than or equal to 0, but x cannot be 5. That's how you would write it in interval notation, something like that, okay? Or sorry, that's set notation, sorry. Interval notation would go something like this. I'm going to go to 0 from 0 to really close to 5, but it can't be exactly 5, union really close to 5 to infinity. Okay, so that's how that goes. You're not including the number 5. So this is what your answer would look like in either set or interval notation for that problem. Okay. And then one more. This has to do with an area of an equilateral triangle. So because this is put in real life context, you can't just look at it algebraically, but you have to think about the context that it's in and think about what happens there. So it says that S represents the sides of a triangle. Well, sides of a triangle can never be a negative number, even though in this equation I could take any number and square it, whether it's negative, positive, fractions, decimals, square roots, it doesn't really matter. I could take any number and square it algebraically, but because this is in context and S represents sides of a triangle, S has to be greater than 0, okay? It can't even be equal 0 because you can't have, if you have 0 length, then you don't have a triangle. So that's what the domain would look like in either set or interval notation. I should clean this up a little bit and make it look like that. Okay. And then range is your y values. The easiest place to go is to look at your graph and see where there's places that the y values don't exist or do exist and kind of go from there. You can also sometimes think about these algebraically, but it does sometimes get a little hard. Okay, this one, if you graph it, you will get a graph that looks something like this, so you can kind of see what's happening. If I draw a line and I look at what my y values are along this line, and I move up and down here, okay, my y, I'm hitting the graph every place, and this is really zoomed in, except for where y values are 0. Okay, so what I also want you to think about is this. If you continue to put numbers in for x, okay, so let's say I put really big numbers in for x. So I move off the edge of this graph right here, and I continue to put really big numbers in for x. So I want you to think about this. If I do 2 over a really big number, okay, so let's say I have 2 over 1,000, 2 over 1 million, 2 over 1 trillion. That's going to be like 0.00000, right? It's getting really close to 0, okay? If I do 2 over a really small number, so now I want to think about it as I'm moving over here, 2 over a really small number, and by the way, it's negative, okay? A really small number, and it's negative. Yeah, well, you guys can think about that, but your range is your y values. Okay, 2 over a really small number is going to give you a really big number. Okay, 2 over a really small number is going to give you a really big number. Then it's going to go negative, and then it's going to go here. Okay, I should have done this. A really small number means I'm going to get closer and closer and closer to 0. Okay, as I do like 2 over 1/2. 2 over 1/2 would be 2 times 2, which is 4. 2 over 1/4 would be 2 times 4. It's a dividing rate, which is 8. 2 over 1/100 would be 2 times 100, which is 200. So you can see 2 over a really small number is going to give you a really big number. That's kind of what's happening over here. And then the reverse happens in this section over here because they are negatives, but you're still doing really big and really small negative numbers. And so that's just kind of what's going to happen. Anyway, you can tell by the graph that your range is every value except for 0. There's a horizontal asymptote at 0. Okay, so your range will go from negative infinity to 0, and then again from 0 to positive infinity. Okay, or set of a y such that y is less than 0 or y is greater than 0. But it can't be exactly 0. Or the easier way to do that maybe would be to say y can't be 0. Okay, it can be every number but 0. So several different ways you can list that. You decide what you like. And that should do it for that lesson.